So we did our review about mole conversions, molar mass, mole to molecule conversions, all that kind of stuff in preparation for Chapter 9. So this is our start to Chapter 9, something called stoichiometry or mole conversions. Okay, you'll hear people say that this topic is difficult. It's not. Okay, if you can plug things into a T-chart, you'll be golden. Okay, this chapter is very simple if you can think your way through it. Okay, so we're going to start with talking about something called a mole ratio. Okay, so a mole ratio is the conversion factor between any two substances. Okay, we've talked about conversion factor between grams and moles, which is, what's our conversion factor between grams and moles? Molar mass. Good, molar mass. And what's our conversion factor between moles and molecules?
Avogadro's number.
Avogadro's number. Good. So now we have a conversion factor between moles and moles of two separate substances. Okay, this is very, very important. Whenever you're trying to differentiate two different substances, two different compounds, you have to have them both in moles. Okay, you can't convert water to oxygen in our gram formula. Okay. So I guess the overall reason that we need to start looking at mole ratios is because Chapter 9, or this stoichiometry chapter, has to do with quantifying our chemical reactions, okay, giving them a quantity. So if I put in 10 grams of some substance, how many grams of my product will I get out? Okay, or if I start with 4 moles of my reactant, how many moles of my product will I get out? Okay, so we're trying to look at perfect chemical reactions and putting a quantity to them. Okay. So we need to start looking at mole ratios, and the only way you can switch between your product and your reactant, or two products or two reactants, or anytime you want to look at quantifying two different substances, you have to be in your mole to mole or mole ratio step. Okay, and we'll explain that as we go along. So let's look at this reaction between potassium chlorate. Okay, what type of a reaction is this? Decomposition. Okay, we started with a big molecule. We break it down into two smaller molecules. Okay, so before we can start any sort of mole ratio stuff, any sort of stoichiometry type work, we have to balance our equation. Okay, that's why we worked so hard with balancing equations, because we have to make sure that we have a balanced equation. Otherwise, our quantification of our substances won't make any sense. It won't work. Okay, so is this equation balanced? Let's just look quickly here. How many potassiums on the left side? 2. How many potassiums on the right? 2. Chlorines on the left? 2. Chlorines on the right? 2. Oxygens on the left? 6. Oxygens on the right? Okay, so we have a balanced equation. It's a decomposition reaction, so we're going to look at what we call the mole ratio between potassium chlorate and oxygen. Okay, what's our mole ratio between potassium chlorate and oxygen? When we look at mole ratio, we're looking at the coefficients in front of that compound. Okay, we know that a coefficient is a number that will give us a relative number of moles. Okay, if I have how many moles of potassium chlorate do I have? How many moles do I have? 2 moles. I have 2 moles, because that's what our coefficient tells us. So my mole ratio is 2, and then how many moles of oxygen do I have? 3. So my mole ratio is 2 to 3. You can write this mole ratio a lot of different ways. We're going to write it as a part of our T-chart, so we're going to write it as in a fraction kind of a form. So we'll say 2 moles of KClO3 is to 3 moles of O2. Okay, and either one could be on top, either one could be on bottom. It makes no difference. It just depends on how you need to enter it into your T-chart. Okay, yeah, Tommy?
So why would you do 2 KClO3 over 2 KCl?
Yeah, you could. You could. If you were trying to look at the mole ratio between these two compounds, you would.
Oh, we're trying to find. Look at the question.
So we're just looking at mole ratio between these two compounds. Okay, and you could do it for any combination of 2. Yep. Good. Okay. So our mole ratio is 2 to 3. In this reaction, it takes 2 moles of potassium chlorate to be put in order to get 3 moles of oxygen out. Okay, that's what our mole ratio tells us. These coefficients tell us. We can also look at these coefficients on a molecular level. Remember, if we look at its very, very smallest form, it takes 2 molecules of potassium chlorate to decompose and form 2 molecules of potassium chloride and 3 molecules of oxygen. Okay, you could look at it on a molecular level or on the molar level, which is a lot bigger quantities. Okay, we will talk about molar quantities more often. Okay, bigger. We're looking at bigger substances here. Okay, does that make sense? Okay, so in this reaction, it takes 2 moles of potassium chlorate in order for us to make 3 moles of oxygen. Is that kind of clear? Remember, what goes in must come out. We've got to have that law of conservation of mass satisfied. We clear so far? Okay. So let's take a look at this reaction. First and foremost, we have to balance it. Okay, so I'm going to zoom it in a little bit here so you can see it better. Maybe. We want to balance our equation first, and then we're going to look to find a mole ratio. Okay, I'm going to zoom this in a little bit. All right, stop freaking out. So first and foremost, you need to balance this equation, and then I want you to try and find the mole ratio between copper and silver.
1 to 3.
Okay, so our mole ratio is 1 to 3. So give me your balanced equation.
1 Cu plus 3 Ag NO3 yields 1 C NO3 2 and 3 plus 3.
Okay, does everyone agree with that balanced equation? Not quite. All right, let's try it again.
Okay, good.
1, 2, 1, 2. All right, that's all right.
Okay, I thought it was wrong.
So 1, 2, 1, 2. That's all right. Are we now? When we're in agreement? Okay, so our mole ratio should then be
2 to 4. Simplified 1 to 2. 33.
1 to 2.
1 to 2. So 1 to 2. Our mole ratio is 1 to
It
2.
doesn't matter which one you put on top.
Nope, doesn't matter which one you put on top. It will depend when we put it into our T-chart, and I'll show you that. Okay? We're going to try what we call mole-to-mole conversions. These are our easiest problems, okay? These are if we are given an amount of substance in moles, and we want to determine another amount of substance in moles of one of our other compounds, okay? So these are our easiest type of problems, going from moles to moles, okay? What?
Easiest problems.
Mm-hmm. Okay. These mole-to-mole conversions, we're going to be given a certain amount of substance in moles, and we want to find the number of moles of a different substance. Maybe one of our reactants or one of our products will be given that.
Not just plain H2O.
Oh, I'm sorry, I'll zoom it back out.
Okay.
It's okay. You're fine. Good for getting
Thanks.
That's Li. Okay.
All right, let's see what our balanced equation here is. Anyone have a volunteer? Yeah, Isaac, go ahead.
1, 2, 1,
1, 2, 1, 1. We agree? Yeah, we agree? Okay. So, we want to try and figure out how many moles of lithium hydroxide, how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide. Okay, so if we want to get these certain products in our balanced equation, which here's our balanced equation, we have a 2 there. In this double displacement reaction, did you guys identify that? What type of reaction it was? Yeah, double displacement. Okay, so we want to figure out how many moles of lithium hydroxide are required to react with 20 moles of CO2. Okay, so here we're looking at both of our reactants. We want to see how much total it's going to take in our reactant side to yield 1 mole of each of these products. Okay, are we clear on what the question's asking?
Not really.
Okay, let's say that we start our reaction with 20 moles of carbon dioxide. So we have to try and figure out how many moles of lithium hydroxide we need in order to get our products.
Okay, that makes sense.
Okay?
Okay, I just was looking at that.
Got it?
Would that be
Well, we're going to work through it, and then we'll look at it. Okay? So we're given 20 moles. That's what we're looking for, or that's what we're told. Yeah, Isaac, do you have a question?
so you only take like
All right, so if we want to find out moles of lithium hydroxide, but we're given a starting amount of carbon dioxide, we're going to start by writing our 20 moles of CO2. Now it becomes increasingly important to keep this label in our T-chart, okay, because we're working with two different substances here. So we have to keep that CO2 so you don't get the numbers mixed up. Okay, we got to keep that label in our T-chart. So we wrote what we know. We want to go from moles of CO2 to what? Good, moles of lithium hydroxide. So we want to cancel moles of CO2, which means it needs to go on the bottom. We want to go to moles of lithium hydroxide, so that can go on top. Okay, are we clear up to this point? Okay, we started with moles of CO2. We want to get rid of it, so that needs to go diagonal, remember, so they can cancel. We want to get 2 moles of lithium hydroxide. That's where our goal is to be, so we put that on top. So tell me the mole ratio between lithium hydroxide and carbon dioxide. Nope. We're just looking back here at our...
That was a joke. So 1 to 2.
I'm kidding.
1 to 2, okay? Once you get to this step in your T-chart, you look back at your coefficients from your balanced equation. Okay, listen carefully. Once you get to this step of your T-chart, you're done with what was given to you in the problem. You're looking back at your chemical equation. Okay? So 1 mole of CO2 to 2 moles of lithium hydroxide.
That makes sense. Yeah, so it would be
Yep.
40.
So we're done with CO2. We canceled that. We're ending up with moles of lithium hydroxide, which is what we want. So now we multiply across the whole top, divide by the whole bottom, and that gives us 40 moles of lithium hydroxide. For this specific chemical reaction, if we put in 20 moles of carbon dioxide, we have to put in 40 moles in order to get our desired products. Okay? We have to do that. All right? Can anyone kind of see now, if we put in 20 moles of carbon dioxide and 40 moles of lithium hydroxide, how many moles would we get of lithium carbonate? How many moles do you think we might get? 20. 20. Because look, the mole ratio is 1 to 1. So if we put in 20 moles, we should get out 20 moles. Yeah. 20, 40, 20, 20. Okay? And we'll work through that. I just want you to start seeing kind of the process of it. So if you don't see it yet, that's okay. We're going to work through that. Okay? Let's try another one. This works through our whole process of it. No, this just works through exactly what we did, so people that have to do it online can look at it. All right. How many moles of O2 will result from the decomposition of 5 moles of hydrogen peroxide? Okay? So, too much talking, okay? First of all, let's go ahead and balance this equation. And then we'll start working through our T-chart. All right, so what's our balanced equation? 2, 2, 1. Good, 2, 2, 1. Okay, so we want to try and figure out how many moles of oxygen will result from 5 moles of hydrogen peroxide. Okay, so the first step in our T-chart is to just write what we know. Okay, what do we know from this problem?
2 to 2 in 2 different ratios.
But when we write what we know, we go straight from the problem.
5 moles.
So we know 5 moles of hydrogen peroxide. Okay, we don't look at the chemical reaction until our mole ratio step. Okay, so we start with 5 moles. What's hydrogen peroxide? H2O2. That's our hydrogen peroxide. H2O2, right? And if it's the one decomposing, then we know it has to be this one. Okay?
That stuff helps with acne.
Uh-huh. That's what you put on cuts and it foams up and it stings.
Yeah.
Okay?
It's a fiber.
Listen. Okay? If I want to get rid of moles of hydrogen peroxide, where do I put it?
On the bottom.
Put it on the bottom. So moles of H2O2. And then I want to go to what? Moles of O2. So now this step right here, we have to look at our mole ratio. So tell me from the chemical equation, what's our coefficient for the oxygen? 1. And our coefficient for hydrogen peroxide is? 2. So I'm getting rid of moles of hydrogen peroxide. Those cancel out. I'm going to multiply across the whole top, divide by the whole bottom, and get
2.5.
2.5 moles of what?
O2.
Okay.
That makes sense.
Okay, any questions there? Okay. You want to say hi to Elizabeth?
Yeah.
Hi, Elizabeth.
Okay, that's too much.